Okay, today we are talking about trigonometric functions of right angles or acute, or not right angles, acute angles. Um, and so we're going to talk about those acute angles, and we're going to start putting trig functions and angles on the coordinate plane. Okay, so one of the key things to the coordinate plane is standard position. Standard position of an angle based on a line, and the angle is always measured to the positive x-axis. Going counterclockwise or through quadrant 1, 2, 3, 4. So I'm going to label the quadrants in case you're forgetting that. Going across 1, 2, 3, then 4, which is a counterclockwise direction, is positive angles. If I go the other way, it's negative angles. We'll get to that more in section 4.3. But all of ours right now are going to be in quadrant 1. The angle will always measure to the positive x-axis, not to the y-axis. You're never measuring an angle to the y-axis in trigonometry. Okay, and hopefully you've heard SOHCAHTOA before. It's a little way of helping us remember our trig functions. That sine of some angle equals opposite over hypotenuse. So cosine of some angle, c, equals adjacent over hypotenuse, and tangent equals opposite over adjacent. Those are our three basic trig functions. They're on the face of your calculator, and they work. We also have what's called the reciprocal trig functions. And I have them written out purposely in the way they are. Cosecant of theta is hypotenuse over opposite. Cosecant of theta is the reciprocal of sine of theta. Yes, this is CSC stands for cosecant. And yes, cosecant goes with sine. This is not the inverse sine. The inverse sine will get me the angle. We'll use that later. That gets me the angle. And actually, you don't take the inverse sine of theta. You take the inverse sine of opposite over hypotenuse. We get an angle. So sine to the -1, I know to the -1 power means 1 over. In this case, it does not. Secant is the reciprocal of cosine. Notice how when I write my 6 trig functions, I specifically write them the way I wrote them here because sine and cosecant go together. Cosine and secant go together. I don't have an answer for why cosecant goes with sine and secant goes with cosine, other than somebody named them that way. Secant is the reciprocal of cosine. Again, it's not the inverse cosine. Cotangent, and again, these are abbreviations. You will say the whole word. You will call it sine, not sin. You'll call it cosine, not cos. Tangent, not tan. Okay, we're going to pronounce them correctly. Cotangent, not cot. Cotangent is the reciprocal of tangent. Okay, so we're going to apply these to a couple of our special right triangles. And we're going to start with our most basic one, the isosceles right triangle, which has angles 45, 45, and 90. Sometimes we call it the 45, 45, 90 right triangle. And you should know from geometry that these are x, x, and x square root 2. I'll show you that in a second. Isosceles means the two sides have to be the same. So using the Pythagorean theorem, x squared plus x squared equals c squared. 2x squared equals c squared. I square root both sides. I don't need the plus or minus here because I can't have a negative length. And then my square root, I can square root the x squared and have x, but I cannot square root the square root of 2, so it's simply x square root of 2. So when I do the sine of 45 degrees, we get opposite. We'll take this 45 on the lower one, opposite across from this x. So it's adjacent. And x square root 2, giving me the x's cancel out, I get 1 over square root of 2. Well, I don't like 1 over square root of 2. I'm not allowed to leave radicals in the denominator. So I shall rationalize. I do that by multiplying the top and bottom by square root of 2. The square root of 2 over square root of 2 is what we call a clever name for 1, because it equals 1. And I can multiply anything by 1 whenever I want, giving me on top the square root of 2, and the bottom square root of 2 times square root of 2 is 2. Why did I choose this name for 1? Because it gave me a rational number, or a regular old number, a 2 on the bottom. Now we'll do the cosine of 45. Again, that's x is the adjacent, and x square root 2 is the hypotenuse. Oh, hey, I know that that rationalizes the square root of 2 over 2. I just did it above, so I don't need to do it again. The tangent of 45 is x over x. That's just 1. Okay? So there's my 3 basic trig functions for 45 degrees. And we want exact answers, which means you do not use a calculator. Your answer better say, for cosine of 45, square root of 2 over 2. If it asks you for exact, it better have the square roots in it. Same with sine. Tangent, you're going to get the same thing. You'll get 1 on your calculator, so it doesn't matter that much. The cosecant now of 45 degrees. I'm going to do the reciprocal. I'm going to use this one for the reciprocal so that I don't have to rationalize. I would get the same thing if I used the other one and rationalized, but I like to do it the easy way. Square root of 2 over 1, that's simply square root of 2. The secant of 45 degrees, well, if the sine and the cosine were the same, the secant and the cosecant, their reciprocals, will be the same. And the cotangent of 45 degrees equals the reciprocal of 1, which is just 1. If you'll notice, all of these x's canceled out. So when I do the 30, 60, 90 right triangle, that's our other special right triangle, I'm just going to make all the x's 1. $30 is here. 60 degrees is here. 1 square root of 3, and 2 times 1. So this is a little trick, just dropping the x's, because they all cancel out when I'm doing these trig ratios. And it works out pretty easily. So the sine of 30, opposite over hypotenuse. Opposite the 30 degrees is a 1. Hypotenuse is 2. Cosine of 30, adjacent to the 30 degrees is square root of 3. Hypotenuse is 2. Again, these are the exact values. I need to leave them as exact values. Tangent of 30 degrees, 1 over square root of 3. I must rationalize. So my clever name for 1 here is not square root of 2 over 2. That doesn't help. But it's square root of 3 over 3. because square root of 3 times square root of 3 is in fact 3. So my rationalized version is 1 over square root of 3. We'll do my cosecant. 2 over 1. My secant. 2 over square root of 3. Again, I must rationalize. So I'm multiplying by square root of 3 over square root of 3. 2 square root of 3 over 3 for the secant. And the cotangent, again, I'm going to take the unrationalized one and flip that for my reciprocal. Square root of 3 over 1, which is square root of 3. We can also do these for 60. And I'm going to point out a connection here. Sine of 60. Square root of 3 over 2. Cosine of 60. Adjacent to the 60 is 1 over 2. Tangent of 60. I am doing these in degrees, not radians right now. We can also do them in radians. Square root of 3 over 1. Cosecant. Reciprocal of 2 over square root of 3. I already did that one rationalized, so I'm going to just call it 2 square root of 3 over 3. Secant of 60 equals 2. And cotangent of 60, reciprocal of 1 over square root of 3 is, or the square root of 3 over 1 is 1 over square root of 3, which I rationalized before to square root of 3 over 3. And we can see the sine of 30 is equal to the cosine of 60. The cosine of 30 is equal to the sine of 60. The tangent of 60 is equal to the cotangent of 30, and the cotangent of 30 is equal to cotangent of 60. And yes, this applies also to the cosecant and secant. The ones we most commonly use are the sine and cosine. That's a very useful trigonometric identity later on. Okay. So those are our two special right triangles where we must have exact answers. We're going to deal with another one where we're going to have all exact answers. And I'm going to ask you for what are the 6 trig ratios? And I'm going to tell you one of them. I know theta, I also know theta is an acute angle. So I know theta is in the first quadrant. That's all we're dealing with today. 5/6. So I'm going to draw this out in the first quadrant. 5/6. That means opposite is some multiple of 5, and hypotenuse is some multiple of 6. I'm going to just take the least common multiples. And I'm going to get this third side, x, with the Pythagorean theorem. Oops. X squared plus 5 squared equals 6 squared. That's an equals. So x squared plus 25 equals 36. I'll subtract 25 from both sides. And I get x squared equals 11. X then is equal to the square root of 11. So I know one of my trig ratios. I'm just going to write it out because it's helpful. I'm supposed to find the other 5. Oops. I could find my angle. We'll do that in a second with a calculator. But sine of theta equals 5/6. Cosine of theta equals, theta is right here, always. So the adjacent side is square root of 11 over 6. The tangent of theta, opposite over adjacent, 5 over square root of 11. I must rationalize. This one, my clever name for one is going to be square root of 11 over square root of 11, giving me a final answer of 5 square root of 11 over 11. Cosecant of theta. Again, I do my reciprocals. Secant 6 over square root of 11. Again, I rationalize the same way, giving me 6 square root of 11 over 11. And cotangent of theta. Again, I'm going to use my unrationalized one when I do the reciprocal. Square root of 11 over 5. If you used your rationalized one, you can rationalize it and still get it back, but you just have to reduce. If I want, I'm going to use my original. If I want the angle, I know here that sine of theta is 5/6. I'm going to use the inverse sine. And the angle I can only get an approximate with my calculator. Okay, so a couple of things about the calculator. So, first thing, we must be, if we're doing degrees, we must be in degree mode. So I'm going to go to mode, go over to degree and hit enter. And then I'll do second mode to quit, or second quit. Inverse sine, 5 divided by 6. If there's nothing after it, it doesn't matter if you close your parentheses, but it's a really good habit to get into because sometimes we'll have like sine of something plus something else. We have 56.44. Never use this inverse sine here to do a cosecant. If you want to do a cosecant, you have to do 1 divided by sine of 5/6. And I could compare this. If I wanted to check my answers right, I get 68.7. No, that was wrong. 1 divided by sine of, I actually need to use that angle, 56.44. I didn't have the angle before. It's like, this doesn't look like it's working out. I need to use the angle, not the ratio for the sine. 1.2. And 1.2, 6/5. Yeah, that's 1.2. So yes, you can check them by checking the calculator and checking that your exact answers are the same. Okay. Now we're going to talk about solving a triangle and then doing a word problem. Right triangle trig word problems are relatively easy. So we have a right triangle with a hypotenuse of 8 and an angle of 37. Solving the triangle means getting the rest of it. 8, 37. Let's make that a much nicer 3. I know that my 3 angles of a triangle add to 180. And I've got this one here that's 90 in the corner. So my other 2 add to 90. So I can just do 90 minus 37 to get the other angle, and that's 53. Now, we'll call these X and Y. To finish solving the triangle, I need x and y. I know that the sine of 37 is equal to y over 8. So to solve this, I do 8 times sine of 37, which is going to equal my y. And that is, I use my calculator, I do 8 times sine of 37, I get approximately 4.81. To get x, sure, you could use Pythagorean theorem. I think it's easier to just go to the cosine and do x over 8. 8 cosine 37. And I multiply both sides by 8 to get it out of the denominator. And I get 6.39. When I solve triangles, I write my things right on the drawing of the triangle. Makes it easiest to see. Solve a triangle means get all the missing pieces. So all the angles and all the sides. Finally, we're going to use this to find the height of a building. So this is an indirect measurement of height using trigonometry. Here's my building with its kind of large with giant windows. We are standing 340 feet from the building, looking up to the top of it with what's called an angle of elevation. That's the angle looking up of 65 degrees. I don't know why I wrote a 3. The distance from the building is 340. So to get the height, that's an opposite side of the 65. 340 is adjacent, so I'm going to use a tangent. And I get tangent of 65 equals opposite over adjacent. To get the 340 out of the denominator, I multiply both sides by 340. And this gives me a value of approximately 729 feet. And I'm using the squiggly equals for approximately. Okay, that is it for section 4.2.